Yeah, welcome back. In this particular video lecture, we will talk about water cooled condensers and a little bit on the evaporative condensers as well. Okay, but the majority of the portion is on water cooled condensers, so I have titled it as water cooled condensers. Okay, so in this case, obviously the condensing medium is going to be water. The advantage of using water is that, the heat carrying capacity of water is more. Okay, water being a liquid, it is capable of carrying large amount of heat, and then it is capable of getting converted into vapor form as well. Okay, because of that, you will be able to have both the sensible heat as well as the latent heat. So the heat carrying capacity of water is more. Whereas in case of air, you will be able to have only sensible heat removal. In water, you will be able to have both the sensible heat removal as well as the latent heat removal. So water is the condensing medium here. And based on the adequate supply of water that is available and the drainage system that is available, you can have two different types of water cooled condenser for two different sites systems. One is for the wastewater system. The other one is the water recirculation system. So if you are going to use the wastewater system, and I say the wastewater system, you have ample amount of water that is available from the city mains, the city mains in the sense where you get the supply of water. So you have adequate supply of water from the city. And once that water is used in the condenser, it is then sent back to the sewer systems or the drainage system. Okay, it is just sent back to the channels through which the water is drained in the city. Okay, so that kind of system is what we call as the wastewater system. Hot vapor refrigerant that is entering into the condenser, and the refrigerant, it gets converted into liquid refrigerant, it is taken back to the receiver so that it is sent to the expansion valve. And you can see the water cooled condenser over here. I take water from the city mains, it is taken to the condenser. It cools the refrigerant. It converts it from the vapor refrigerant to the liquid refrigerant, and the hot water, the warm water that is sent to the sewer lines. Okay, so that is your water cooled condenser, which uses the wastewater system. There is another system which doesn't waste the water, but it uses the water economically, and it conserves water, let me say, where we call it as the recirculating water system. So what we do here, you can see the same vapor refrigerant that is entering into the condenser and leaving as the liquid refrigerant to the receiver so that it can be sent to the expansion device for further expansion, so that the temperature as well as the pressure reduces. And you can see the cold water in to the condenser, and that water is not drained to the sewer lines. Rather, the warm water is taken to the cooling tower again. So in this case, by self-evaporation, it cools in the cooling tower, and that cold water is again pumped to the condenser. So you use a cooling water tower, a cooling tower. Okay, and then you can see that it is the water from the cooling tower is pumped back to the condenser. And of course, in some amount of water gets evaporated, and to make up for that loss of water by evaporation, okay, a makeup water can be added to this particular condenser water line. Okay, so this system where water is not wasted into the sewer lines and where it is recirculated in cooling tower, and sometimes people also use spray ponds. Okay, so that is what is mentioned over here. They either use the cooling water towers or the spray ponds as the water cooling devices, and the warm water is cooled over here and it is pumped back to the condenser. The water is not wasted, it is conserved. And so it is called as the recirculating water system. Okay, so that is your water cooled condenser. Right. And what are the points that needs to be noted? The water cooled condensers, they operate at low condensing temperature than that of the air cooled condensers. And the supply water temperature is usually lower than the ambient air temperature. However, the difference between the condensing medium and the cooling medium, that is almost 400 degrees centigrade, which is same as that of the air cooled condenser as well. And one advantage is that the compressor which we use in case of a system where water cooled condenser is used, it requires less power for the same capacity. Because your water cooled condenser, it removes a large amount of heat and it converts the refrigerant back into a refrigerant liquid. And so, the compressor capacity, the power that is used for running the compressor, that is a little bit less in case when we use the water cooled condenser. Okay. And then you have different types of water cooled condensers, and all these are heat exchangers, okay, which you would have already done in your heat and mass transfer course. So we use tube and tube or double tube condenser. That is what people also call as the double pipe heat exchangers. So either you call it as double tube or you can also call it as double pipe heat exchanger. So that is a pipe within a pipe. And then you have shell and coil condenser. You have a shell, and inside it you have a coil. So that is called shell and coil. And then you have shell and tube condenser. So you have shell, and inside it you have either a single tube or usually tube bundles where you have multiple tubes placed inside it. So those are called as shell and tube condenser. So let's look at one by one. So what is shown in this particular slide is the tube and tube condenser or the double pipe condenser. So you can see there is one tube which is shown as shown with a blue color line, and there is another tube which is shown with the red dots. That is another tube. Okay, so you can see the hot water refrigerant entering from the compressor through this non-shaded blue color tube. So this vapor refrigerant, it enters and it flows through the tubes, and then it finally comes out as liquid refrigerant. And what we have here is the cold water that is entering in, and it goes through these tube. So you can see that there is no contact, there is no mixing between the refrigerant and the water that is used here. So what is done here is the cold water is passed through the refrigerant that is flowing through these tubes. So the refrigerant, the tube that passes the refrigerant, that is the outside one, and the tube that is carrying the water, that is what is the that is placed inside the tube that is carrying the refrigerant. Okay, so that is a tube and tube. So the outer tube carries refrigerant, the inner tube carries water. Okay, so the water is capable of removing heat from the refrigerant as it goes out. And it also follows your natural convection principle also, wherein when you absorb heat, the density of water becomes less a little bit, and so it is easy for the water to rise up. Okay, obviously it is not going to rise up on its own. You are going to use a pump to do that. Okay, so however, so the water flow is from bottom to top and the refrigerant flow is from top to bottom. Okay, and that is what is mentioned over here. The other point could be here is it can be either a parallel flow system or a counter flow system. What is shown here is a counter flow system. You can see water moving from bottom to top. And let me use another color over here. So let me use blue. So you have the refrigerant moving from top to bottom. So the entry of the refrigerant is at the top, the entry of water is at the bottom. So the flow is opposite to each other. So we call it as the counter flow. The advantage of the counter flow is, see, when the hot water, when the hot vapor enters here. Okay, so it is going to be, it's going to be of the higher temperature. That is the highest temperature that is encountered here. Okay, whereas the water that is entering in, that is going to be cold water. This vapor, it loses heat as it comes down, and so it is going to have less amount of heat. So that less amount of heat is easily removed by this water. Okay, and then as it goes up, it further takes heat from a relatively higher temperature refrigerant. Here the temperature is higher, here the temperature of water is lower. So the temperature difference between the water and the refrigerant, that is maintained in every single step. So here the temperature difference is almost the same. The temperature difference is almost the same. The temperature difference is less. The temperature difference is less. The temperature difference is less because water has got lower temperature. This liquid refrigerant is also having lower temperature. Then water acquires a little bit higher temperature. The vapor refrigerant is also coming at a higher temperature. Then further high temperature of water, further high temperature of vapor. So you maintain the temperature difference. The temperature difference does not increase much. Whereas if it is going to be a parallel flow, where you have water entering from top to bottom, and you have if you have water entering from top to bottom and you have the refrigerant entering from top to bottom, you can see that at this in this case the temperature is less. You have a lesser temperature, whereas here you have a higher temperature. Okay, at the entry. When it goes out, here it has the higher temperature, and here it has got a relatively lower temperature. The temperature difference is huge. So when the temperature difference is huge, that is going to affect the heat carrying capacity of water. Okay, so that is not going to result in an efficient heat removal. Okay, so it is always preferred to have a counterflow heat exchanger. The temperature difference between water and the refrigerant, it fairly remains constant. Okay, whereas in the parallel flow, the ability of the water to absorb heat decreases as it passes through the condenser. Okay, so that is your tube in tube condenser. The next one is shell and coil condenser. So you have an outer shell. So what is shown here, this rectangle, this is your shell. The shell has got an entry and it has got an exit. So from the entry, you have the hot vapor refrigerant, and through the exit, you have the liquid vapor refrigerant. Okay, so let me change the color again. So you have the water entering from below. Once again, it is passing through the coil. So in this case, it is a serpentine coil again, and it leaves out as warm water outside. Okay, so this tubing that you have, or which we call as the coil, so it has got some flexibility. So it can either expand or contract due to the temperature changes, and it can also withstand any strain that is arising out of the temperature changes as well. Okay, and you can either place this one horizontally or vertically. The tubes or the coils, you can add fins to it, or it can be just plain. And as usual, you can either have the counterflow or the parallel flow, but the counterflow is preferred. Okay, the only disadvantage that you have is this coil that is placed inside the shell. If it needs to be cleaned, it cannot be done manually. Okay, you can't open it and assemble it again and again. So it is not possible because it will be welded together. So it's not possible to disassemble the system easily. So what you should do is you should use chemicals to clean this coil that is there inside the shell. Okay, so that is one of the major disadvantage that you have here. Okay, so it can be cleaned only with the help of the chemicals. Okay, and then what we have here is it can be used only in units up to 50 ton of refrigeration. Okay, so that is your shell and coil water cooled condenser. Then what you have is a shell and tube condenser. This is just like your shell and tube heat exchanger. You have got shell and you have got these tubings, and these tubes are attached to the tube sheet. You can see this is a tube sheet over here, and the tubes are connected to the tube sheet. You can see the holes in the tube sheet where your tubes can be fixed or welded together. Okay, and you can also see water boxes over here. It is through which water enters in and water leaves out. Okay, so this is actually a double pass condenser. So you have water entering through this, and then you have the water going out through this. So it passes the shell two times. So it's a two pass. It's a double pass, two shell pass condenser. Okay, so it is passing the shell two times. Okay, so it's shell and tube condenser over here, and you can see that people normally use baffles in order to avoid the bending or sagging of tubes here, because they are very lengthy. In order to provide support, people use baffles, or you can have any type of intermediate support for that matter. Condenser tubes, again, once again, the tubings, it can be either steel or copper, and you can either have fins or without fins, whichever is convenient without your budget and with the requirement that is specified. You can have all these parameters that come into play. Okay, and in case of ammonia, we have already seen that the copper tubes, they get corroded when ammonia is used as a refrigerant in the ammonia refrigeration system. And so people normally use steel tubes, and that too without fins. Okay, so that is how shell and tube condensers are used in case of ammonia refrigeration system. And you can see the difference between air-cooled condenser and the water-cooled condenser as mentioned by Kurmi in his textbook. So the construction is simple in case of the air-cooled condenser. So the initial cost is going to be low and the maintenance cost is also less. Whereas here the construction is a little bit complicated. And because the construction is complicated, you're going to have a higher initial cost and the maintenance cost is also going to be high. So the handling problem, there is no problem in handling the air-cooled condenser, but it is a little bit difficult to handle. And the maintenance is also a little bit difficult. Okay, and here it doesn't require any piping arrangement for carrying air. because air, once it is going to get heated by the warm air, tends to rise up very quickly. Okay, whereas the cold, so you just need a fan to blow the air. Whereas here you require pipings to take water. So piping means additional material needs to be used. So that is going to add to your material cost. So no problem in disposing air. Air can be taken in, air can be rejected to the ambient. But here you need a recirculation system, you need a cooling tower, then you need a pump to pump back to the condenser. So the recirculation system is required. So there is going to be no corrosion or fouling effect in case of air. Once again, depending upon the purity of water, you may have fouling effects due to the corrosion. Then you have the disadvantage that you have is the heat carrying capacity is very low in case of air, and the heat carrying capacity of water is high. Okay, and it is air is used in low capacity plants, whereas water cool condenser can be used for large capacity plants. Power required to dry the fan is high, and so the noise it cannot be avoided. So here there is no use for fan at all. So there is no fan noise here. So it's a little bit quiet over here. Distribution of air is not uniform in the condenser surface. Okay, whereas because with the reference to the flow of air, that depends on the speed with which the fan blows it. So there is a possibility that some air may bypass the coils. Whereas here you have even distribution of water on the condensing surface because the water is going to flow through the tubes. Okay, and then you have high flexibility in case of air-cooled condenser, whereas that sort of flexibility cannot be expected in case of the water-cooled condenser. So the difference that has been given very well represented and very well given by Kurmi in his textbook. So this is what the water-cooled condensers are all about. Okay, and then what we have is the evaporative condenser. So the evaporative condenser, as I mentioned earlier, it is going to use both air and water as the condensing medium. So I want you to draw your attention to this picture over here on the left-hand side of the slide. So you can see that there is a water pool, which you can also call as a sump of water. Okay, so I have my condenser over here. Okay, so the refrigerant, it has taken, it's the inlet of the refrigerant is here and the exit of the refrigerant is over there. It can be other way around too. You can have the refrigerant inlet at the top and the refrigerant exit at the bottom. And what I have here is the water from the sump. It is pumped over here to the sprayers or the spray headers, however you call it. So it is supposed to be sprayers, and you can also call them as spray headers. These spray headers, so this is the spray header, and this spray header has got nozzles over here. The opening is what we call as the nozzle. So through the nozzle, water is going to be sprayed over the condenser coil. Okay, and as the water is sprayed over the condenser coil, the water is going to pass over this condenser coil and it is going to remove heat from the condenser coil. Okay, so as it moves over the condenser coil, the water evaporates by absorbing heat. Okay, and what happens here is, and some of the water it gets condensed. So water droplets can be seen on the condenser coil surface. And what we do is we also have fan at the top. So you can see this is the fan over here. So two fans are mentioned here. So either it can be a single large fan or a multiple fans. This fan, it sucks in air through these openings, and the air is taken in. And this air, as it blows past the condenser coil, it carries the water droplets, whichever is settled over here, it carries them away. Okay, so as it carries them away, so it's like the principle, like when you take a bath and stand under a fan, or you feel cold. Why do you feel cold? The air that passes over your body, it removes the heat from that body. And in the meantime, that heat removal converts the water droplets that is present in your body into that water droplet, it gets converted into a vapor form. So a similar situation arises here. The air carries away the water, so the latent heat of vaporization is removed from the surface of the condenser coil. So that converts your refrigerant vapor into refrigerant liquid. Okay, the water removes heat. In addition, the air also carries away the heat. And in addition to that, you will have something called as an eliminator over here. So the eliminator is something like a filter. It makes sure that the water droplets, they do not pass along with the air. It filters the moisture content and makes sure that the water content is brought back to the water sump or water pool. Okay, and because we pump this water to the spray headers and the water gets evaporated as it falls down, there may be some loss of water due to the evaporation effect. And for that, you can have a makeup water. Makeup water can be added, and for which people use floating devices. Floats are being used in order to control the supply of the makeup water. And okay, so that is how these evaporative condensers work. Okay, so these evaporative condensers, so it functions, or it performs the operations of both a cooling tower where you have the water being sprayed over the condenser, and it also acts as a water cooled condenser because this water carries away the heat from the condenser surface. Okay, so your evaporative condensers, it acts both as a water cooled condenser as well as a cooling tower, and it also uses both air and water as the cooling medium. Okay, so this is the end of condenser. Once again, the textbook on refrigeration air conditioning by Furmi has been referred to. Thank you. We will meet again in the next unit.